All right, so in this next and final example, what I'm going to do is build up a process for how you can take nonlinear data and fit functions to it using logarithms. So we're given some data here, okay? And first thing I'm going to do is just plot it. All right, so there you go. I plotted the data. Okay, I just took each point and plotted it on my graph and then connected the dots. All right, now you can see it's nonlinear. Obviously, it's not a line. So that's obvious. But we would like to, if we wanted to find a function, a nonlinear function, we want to try to find a nonlinear function that fits this data. That's our goal. Now, there are a number of different nonlinear functions, all right? Here are some examples of nonlinear function. We have an exponential function, or we have a power function, and they, you could see that you could possibly use either one of those types of functions to model this curve that I got here. Okay, it's not obviously clear what would be the best option, So that's the goal, though, is to analyze this data set using logarithms to help us decide and actually come up with a nonlinear function that fits that data. Okay, that's the goal here. All right, so step one, what we're going to do is we're going to transform the y coordinates logarithmically. Okay, we're going to leave the x coordinates alone, and we're just basically going to take the logarithm of all the y values. All right, so I'm taking the data in part A and just taking the logarithm of the y values. So this is what I got. Let's see, I got 2.06, 1.22, 0.74, 0.39, and 0.12. All right, just taking the logarithm of the y values. And now I'm just going to plot that. All right, did I mention, you probably already figured this out, this would be a good set of lecture notes to print because it's a little hard to just sketch things in, on just lined notebook paper. It's also a good idea to have a ruler when you're doing this. Now, I don't have a ruler online, or at least I couldn't figure out how to make it work. So, but if you try to take this, I should also mention too, I noticed that notice the y-axis is the natural log of y. The x-axis is still the x-axis, right? But we're plotting the natural log of y. Okay, so essentially this y-axis is a logarithmic scale, but we're just plotting the natural log. All right, so what I would do now is take a ruler and try to fit this curve, just eyeballing it. Now you could do some kind of linear regression if you wanted to, and do this more systematically. But what I would do for the purposes of these problems is just use a ruler. And if I use a ruler, it's not obvious here, but because I don't have a ruler that I can just. If I tried to draw a straight line between these points, it would, the points don't fit a line very well. Okay, I mean they're close, but it's just data too. So maybe that's could be considered linear, but it's not exactly linear. All right. So the next step in the process here is to transform both the x and y coordinates logarithmically. Okay, so now I'm going to take the logarithm of both the x and y values in my original table of data. Okay, so that's what I've done. I've just taken all the x and y values in my original data table, and I've taken the logarithm of each of the values. Okay, and then I went ahead and plotted those as well. Notice now I'm plotting the natural log of y versus the natural log of x. So both scales have been transformed logarithmically. And now I want to try and get my ruler out and see how well these data points line up. And if you get your ruler out now, again, it's going to be, I can't draw a straight line as it is on this with this pen, but you'll find if you plot those accurately. And you can draw a straighter line than I can on your paper. But you'll find that those fit those fit a line very, very well. Okay? In fact, they were designed to fit a line very well. So part D says draw a straight line that best fits each data set from parts B and C, which we did, and it's asking us which data set can be best represented with a straight line. Okay, so we look at both of these, and it looks like data set C fits a line better. So, and that is our natural log of x versus natural log of y data. All right, so now we know how to determine the formula of a straight line if we just have 2 points, right? So that's what we're going to do next. We're going to take whichever one of these graphs gives us the best fit to a line, and we're going to take 2 points from that line and come up with an equation for a line. So I know that this data in part C fits a line better. So what I'm going to do is I'm just going to take 2 points, and I'm just going to take 0, 1.22. Okay, it doesn't really matter, but I like having this is essentially the y-intercept or the natural log of y-intercept. So that's a good one to use when coming up with the equation for a line. And then I just need one other point, and I just happen to choose this one. Now you can choose any of them, okay, but choose whatever points you like. All right, so I'm going to just basically take those 2 points, and I'm going to fit a line to those 2 points. Okay, so that's what I'm going to do in part E. All right, so I'm using the points. Oops, again, using the points 0, 1.22. And I'm using the other point is 0.69, 0.39. All right, so what do I need to do? I need the slope, right? So the slope is going to be 1.22, so change in y over change in x, so 1.22 minus 0.39. Change in x is going to be 0 minus 0.69. Okay, when I put that on my calculator, I get minus 1.20. All right, and now I'm going to use the point slope form of a line. Now normally we would write, let me write it up here, it's y minus y1 equals m times x minus x1, right? That's my point slope form of a line, but I'm plotting the natural log of x versus the natural log of y, right? So this is going to become the natural log of y, this is going to become the natural log of x, okay? Because these, and the values of my points are the natural logs of the original x and y values. Okay, so what I'm going to do is I'm going to say the natural log of y minus 1.22 is equal to the slope minus 1.20. And then again, I'm replacing x with the natural log of x, and then the other point is the x coordinate of that point is 0. Okay, so now I'm just going to clean this up a little bit. I'm going to write the natural log of y is equal to minus 1.20 natural log of x, and then I'm just going to add 1.22 to both sides, so plus 1.22. 1.22 is essentially the y-intercept, or I should call it the ln of y intercept. So intercept. So essentially we've got it sort of in y equals mx plus b form, except it's natural log of y equals m natural log of x plus b. Okay, so now we have an equation for the line where both the x and y are transformed logarithmically. All right, one more step. We need to undo those logarithms, and to get, because we want an equation, we want a function in terms of y in terms of x, right? We want some function that looks like y equals f of x. Okay, so we're just going to apply the what we know about logarithms, and get this in terms of y and x instead of natural log of y and natural log of x. All right. So again, I'm just going to rewrite this down here. All right. So natural log of y is equal to minus 1.20 natural log of x plus 1.22. All right. I'm just going to take both sides. I'm going to raise e to both of these equal values. Right. So natural log of y is equal to e to the minus 1.20 natural log of x plus 1.22. All right, this whole thing is the power of e, and I'm just using the equality property of exponents. All right, so now I know that this is just y. E to the natural log of y is just y, and also I have the sum of this exponent here on e is a sum, so I can turn that into a product. All right, I'm going to take this constant here, this e to the 1.22 times e to the minus 1.20 natural log of x. All right, we're getting there. I want to get that natural log of x out of there. So, so now I can calculate this. This is just a constant. I'm just going to leave it as it is now. So e to the 1.22. Now I can, because I have a natural log and then I have this, it's multiplied by negative 1.20, I can use the power property to bring this inside the natural log. Okay, so I get e to the natural log of x to the minus 1.20. And now you can see that I can get rid of the, I've got e to a natural log, and so I can just write that as e to the 1.22, and then this just becomes x to the minus 1.20. Okay. All right. So one more sec. Let's make this into a constant, just a regular numerical constant. So our equation is 3.387. That is what e to the 1.22 is. X to the minus 1.20. Okay. So you can see that in this particular case, it turned out that a power function actually models our data better than the exponential. So if we had, because it turned out that transforming both coordinates logarithmically turned out to give us a better fit for a line, and then that results in a power function. It gives us a power function. We can get a power function that fits our line. Okay, so this is our equation. This is our equation that fits that data. All right. Well, that's quite a process, and it's something that you need to practice. All right. So there's a practice problem in the discussion questions. There's really only two discussion questions, but one of them is a problem very much like this, which we will go through in class. All right, so I will let you look ahead if you want to try some of those discussion questions, try to get a head start on them. That's great, and I'll meet you in class.